Hello everyone. Today we're going to look at inverse relations. Okay, when we have two different relations, now remember a relation is when you have one x variable goes to a y variable. So when you have a relation, an inverse relation exists if and only if that particular coordinate AB would be switched for the inverse. So that means that the coordinate for the inverse would be BA. So your x and your y values, they switch places for inverse relations. If the relations are expressed as equations, you can find the inverse by interchanging the x and the y. And finally, if you have an inverse relation and its function, you can then graph it, and when you graph it, it is a reflection along the line y is equal to x. But you can see graphically right here below, if we have some function here, in the one in like the red, and if it's flipped over that line y is equal to x, that would be its inverse. Now the actual definition of an inverse function is when you have two functions f and g, and if you were to find their compositions, so either f of g or g of f, both of those compositions should equal to x. Additionally, inverse functions are noted in this notation, where you would have f, and it looks like a -1 as an exponent. This represents the inverse of the function f. And then finally, the domain of your function is equal to the range of the inverse and vice versa. And this is because since your x and your y values switch places for the inverses, that means that the domain and range also switch places, since the domain represents the x's and the range represents the y's. Now remember that the definition of the inverse is if your compositions of f and g of f both equal to x. So we're going to prove that these two functions are indeed inverses by finding their compositions. So first we would do f of g of x. So what we do is we're going to take f and we're going to copy it down. And where I have the x, I have my parentheses. And in there, I'm going to go ahead and copy g. So 6 over x plus 4. Now from here, because I can't do anything in this parentheses, I can basically remove it. And I can see that these 4's cancel out. So now what I have is 6 over x. Now this is basically a fraction divided by another fraction. If I were to write 6 as over 1. Now when you're dividing fractions, remember that we copy the numerator, so 6 over 1, and we multiply with the reciprocal of the denominator, which is x over 6. If you ever have the same number in the diagonal, this means that we have 6 divided by 6, which would cancel. Or if you choose to just multiply like normal, when you're multiplying fractions, you do numerator with numerator, so 6x over 1 times 6, which is 6. And then here you can still see that the 6's cancel and we end up with x. So far everything is looking good. But now we need to verify that the other composition, g of f of x, also equals to x. So we have 6 over x minus 4, because this is my x, plus 4. I'm going to need to take care of this section first. So remember that we can copy, change, flip. So I'm going to copy the numerator, flip the denominator, and multiply. Again, I have 6 over 6 in the diagonal. These cancel. So what I have left is the x minus 4 over 1, which is just x minus 4, plus 4. So now those 4's cancel, and I'm left with x. So since both of my compositions equal to x, that means that f of x and g of x are inverses. Let's try this one more time. So first we're going to find the composition f of g. So I'm going to copy down f, so 4x minus 7. And in here, I'm going to put the x plus 7 over 4. This is as if it's 4 over 1. I have these 4's here that cancel. So now what I have is the x plus 7 over 1, which is just x plus 7, minus 7. And those 7's cancel, and I'm left with x. Now I'm going to do g of f of x. So I'm going to copy down g. So x plus 7 all over 4. And in here, I'm going to write f, which is 4x minus 7. Since I can't do anything in this parentheses, we can basically just remove them. So 4x minus 7 plus 7 all over 4. The 7's cancel. And I'm left with 4x over 4. And those 4's cancel. And so I am left with x. So again, I have just verified that f and g are indeed inverses. Now, how do I actually find that inverse function? And I have some steps here for you to follow. First, we're going to substitute y for f of x. So here we have f of x is equal to x cubed plus 1. I'm going to replace this f of x with y, because remember, f of x stands for y. Then, because inverses are when the x's and the y's switch, that's exactly what I'm going to do. I'm going to replace y with x and x with y. Once you've switched, we are now going to solve for y. So the first step would be to subtract 1 to both sides. So now I have x minus 1 is equal to y cubed. And to cancel out that exponent, I would have to cube root both sides. Remember that when you cube root, it is not the same as square rooting. It is a different root, and it is denoted with the radical and then that root number right there at the corner. So this is my inverse, but we have to make sure that we use proper notation. Once you have your inverse, you replace the y with f inverse of x, which is that notation I mentioned earlier. So this is my inverse function. Now we're going to verify that this is indeed the inverse by finding the compositions. And this is a way of checking your answer. So we're going to find f of the inverse and then the inverse of f. So first I'm going to take my function and I'm going to copy it down. So x cubed plus 1. And inside, that's where I write in my inverse, which is the cube root of x minus 1. Now, because everything in the parentheses is cube rooted, and outside the parentheses we have the exponent, that just cancels out. So now what I have is the x minus 1 and the plus 1. The 1's cancel, and I'm left with x. So far, so good. Now I'm going to do this the other way around and have the inverse on the outside. So the cube root of x minus 1. And in here, I am going to copy down my function. So x cubed plus 1. Since everything is underneath the radical, I want to simplify whatever is inside first. Since I can't do anything with the parentheses, you can basically just remove it. So it's x cubed plus 1 minus 1, and that would cancel. So now all I have left is the cube root of x cubed, which the cube root and the exponent do cancel, and I'm left with x. So again, I have verified that my inverse is indeed correct. Let's try this with some other functions. We're going to find the inverse and then verify by composition. So first, you replace the f of x with the y. Now we switch places. And now we solve for x. So first I'm going to add 3 to both sides. And I have x plus 3 is equal to 4y squared. Now I divide by 4. So y squared is equal to x plus 3 over 4. and now I square root both sides. So my inverse is equal to the square root of x plus 3 over 4. Now we need to verify by compositions that this is indeed my inverse function. So first, let's go ahead and do f of f inverse of x. So I'm going to copy down my function, so 4x squared minus 3. And then inside, I'm going to write my inverse, x plus 3 all over 4. Now the square root and the exponent do cancel first. So now what I have is 4 times x plus 3 over 4, and then minus 3. These 4's would cancel. So now I have x plus 3 minus 3. The 3's cancel, and I'm left with x. So again, so far so good. And now we're going to go ahead and do f inverse of f. So now I copy my inverse first, which is the square root of x plus 3 all over 4. And in here, I'm going to copy down my function. So 4x squared minus 3. Can't do anything with the parentheses, so basically just remove them. But what happens is these 3's will end up canceling since it's in the numerator. So we always got to simplify that first. So these 3's, bye. And so now what I have is the square root of 4x squared over 4. These 4's cancel. And all I have left is the square root of x squared, which the square root and the exponent do cancel, and I'm left with x. So far, everything is good. I have verified my inverse, and so we're ready to move on to the next question. So first, I have f of x is equal to 5 over x plus 4. I replace it with y. So y is equal to 5 over x plus 4. Now I'm going to replace x and y. So x is equal to 5 over y plus 4. Now I need to solve for y. So I'm going to subtract the 4 first. And so I have x minus 4 is equal to 5 over y. Now when you have your variable in the denominator, you can't solve for it like that. So we need to remove it from the denominator. And how we do that is by multiplying. So I'm going to multiply y to both sides. Now when you multiply it to the other side, you're multiplying your entire left side by y. So I put it in parentheses. So at the moment, what I have is y times x minus 4 is equal to 5. Now since I want to get the y by itself, instead of distributing and trying to work it out like that, because then we're going to have multiple y's instead, I'm just going to divide that x minus 4 to both sides. And now the y is alone, and this is my inverse. So f inverse of x is equal to 5 over x minus 4. Now I'm ready to start verifying through compositions. So first I'm going to do my f of f inverse of x. So I'm going to copy down my f, so 5 over x plus 4. And in here I'm going to copy down my inverse. Now remember that we have to simplify this part first. And this we basically apply what we know about dividing fractions. So I'm going to copy my numerator, which is 5 over 1, times the reciprocal of the denominator, so x minus 4 over 5. I notice that 5's are in the diagonal, so they cancel. So all I have left is x minus 4 over 1, which is x minus 4, plus 4. So now the 4's cancel, and I'm left with x. Now I'm ready to verify using my inverse and then my function. So f inverse of f of x. I'm going to copy now my inverse, which is 5 over x minus 4. And in the parentheses, I'm going to copy down f, so 5 over x plus 4. Since I can't simplify anything in the parentheses, I can do the plus 4 and the minus 4, which cancels out. And so what I have now is 5 over x. And again, we multiply by the reciprocal. So 5 over 1, my numerator, times the reciprocal of the denominator, which is x over 5. My 5's cancel, and I'm left with x over 1, which is just x. So I have verified that my inverse is indeed the inverse through these compositions. Now, how do we know that an inverse function actually exists? Much like how we use the vertical line test to make sure that a relation is a function, since inverses are the opposite, we're going to use a horizontal line test to check if an inverse actually exists. If your horizontal line passes through the function more than once, such as here, if I draw this horizontal line, I go through 2 points. This means that there is no inverse for this particular function, or rather that the inverse is not another function. If I were to draw a horizontal line anywhere along this graph, it only goes through 1 point, meaning that its inverse is a function. So, how do I determine the inverse from something a little bit more complicated? So if we're given a graph, we can first determine if the function actually has an inverse. For this particular function, if I were to draw a horizontal line anywhere, I do have an inverse. And if I do, then we're going to go ahead and find the inverse. So according to the horizontal line test, as we saw in the previous example, it goes through exactly 1 point no matter where I put a horizontal line. Therefore, I do have an inverse function for this particular function. We're going to use the steps that we used previously to determine what that inverse is. So remember that this is y equals to x minus 1 over x plus 2. So now in order to find the inverse, we're going to replace x with y and y with x. So x is equal to y minus 1 over y plus 2. Now this can be difficult to work out simply because we have 2 y values here. But don't worry, this isn't going to be too bad. What we're going to do first is we're going to remove the denominator from here. So I'm going to multiply y plus 2 to both sides. So now what I have is y plus 2 times x is equal to y minus 1. In this case, before we did not distribute, but now we are. I'm going to distribute this x. So xy plus 2x is equal to y minus 1. What I want to do now is get all of the y's on one side and everything else on the other side. So I'm going to subtract this y over. So now it's away from the right side here. And I'm going to subtract this 2x because I want the 2x to be on the other side, since I only want all the terms with just y on one side. So now my equation is as follows. We have the xy minus y is equal to negative 1 minus 2x. Once you have your y's all on one side, what we're going to do is factor out the y, since both terms have a y in common. When I factor it out, I get x minus 1. And so now to solve for y, I'm going to divide the x minus 1. to both sides. And so we end up with y is equal to -1 minus 2x over x minus 1. This is my inverse. So f inverse of x is equal to -1 minus 2x over x minus 1. Okay, and finally we're going to be determining the domain and range of our inverses. So when we look at the graph, right, we can see what the domain would be and what the range would be. So for the inverse, since our x's and y's switch places, that means that the domain of your inverse is the range of the function, and the range of the inverse is the domain of the function. And we'll practice that in the following example. So here we have the graph of the square root of x minus 4. I can see my graph, I can determine my domain and range. So for my domain, I notice that we start at x is equal to 4. That 4 would be included, so we would say from 4 to infinity. Now for the range, my y values start at 0, 0 also being included, and then it does go up forever, so to infinity. Now let's go ahead and find the inverse. So we have our function f of x is equal to the square root of x minus 4. Remember, we replace f of x with y. And now I am going to switch places. So x is equal to the square root of y minus 4. Now to solve for y, I'm going to have to get rid of this radical first. So I'm going to square both sides. So what I have now is x squared is equal to y minus 4. And then I'm going to add 4 to both sides. So y is equal to x squared plus 4. This is my inverse function. F inverse is equal to x squared plus 4. Now, although my inverse is a quadratic, meaning it's a polynomial type function, we normally think the domain is from -infinity to infinity. However, because this is the inverse of a particular function, your domain is limited to the range of the function. Since the range of my function is from 0 to infinity, that means that the domain must be also from 0 to infinity. And the range would be limited to the domain of the function. So since the domain is from 4 to infinity for my function, my range would be from 4 to infinity. Now, if we're trying to find the domain and range of an inverse function, it is helpful to first find the domain and range of the original function before we begin. So when you're finding the domain, we already know how to find domain algebraically. But for range, you may need to have to remember what your parent function looks like and what transformations were applied in order to figure out what the range would be. So we look at any kind of vertical transformations for the range, since range are the y values. And what I mean by vertical transformations, the only vertical transformation that affects the range would be any vertical translations. So whether it is moved up or down. So you're checking to see if the graph, or rather the function, has a number that is added or subtracted at the very end, either outside of parentheses or outside the radical or outside the rational function. And that would determine your range. So if we're looking for the domain and range of this particular function, this is a radical. So for the domain, we know that x minus 3 has to be greater than or equal to 0. So this is that x has to be greater than or equal to 3. Therefore, the domain would be bracket 3 to infinity. Now for the range, this is a radical function, right? Radicals, as we noticed in the previous slide, which I'll go back to so you can see, if there was not moved up or down, it always starts at 0. Since I don't have a number added or subtracted at the end of my radical, that means that the range is from 0 to infinity. Now let's go ahead and find the inverse and see if we can make sense of the domain and range of the inverse. So remember, y is equal to 2 square root of x minus 3. I'm going to switch places, so x is equal to 2 square root of y minus 3. Now I need to solve for y, so first I'm going to divide by 2. So we have x over 2 is equal to the square root of y minus 3. Now I'm going to square both sides so that that radical can cancel. When you square a fraction, you square the numerator and then you divide it by, you square the denominator. So we have x squared over, and then 2 squared is 4. And that is going to equal to y minus 3. And finally, I'm going to add 3 to both sides. So my inverse is equal to x squared over 4 plus 3. Now the domain and range. Remember that the domain of your function, of the inverse, is limited to the range of my function. So the domain of my inverse is only applicable from 0 to infinity. And for the range is limited to the domain of my original function. So that would be from 3 to infinity. And you always want to check if your domain and range makes sense with your inverse. The domain of any polynomial type function, such as this inverse, is negative infinity to infinity. So consider the range of the function as like your restriction. So this is from 0 to infinity. Now the range, if I look at my equation, I have this plus 3 at the end. That means that my quadratic, which on the graph is a parabola, was shifted up 3 units. And we know that from our parent function, the parabola's vertex, which is the lowest point on the graph, is at 0, 0. So if it moved up 3, that means that we're starting at 3 and then to infinity. Now for b, we have f of x is equal to x plus 2 squared minus 1. So the domain of this, because this is a quadratic, is from negative infinity to infinity. And the range, remember we're looking to see if we have any number added or subtracted on the outside. This means that my parabola was shifted down 1 unit. So it would start from negative 1 to infinity. Now we're going to go ahead and find the inverse. So y is equal to x plus 4 squared minus 1. Let's switch places. So x is equal to y plus 4 squared minus 1. We're going to solve for y, so I need to add the 1 over. X plus 1 is equal to y plus 4 squared. We need to get rid of the exponent, so I'm going to square root both sides. So we have the square root of x plus 1 is equal to y plus 4. And now I'm going to subtract the 4. So my inverse is equal to the square root of x plus 1. And that minus 4 I subtracted later, so it is outside of my radical. Now to find the domain and range. This is a radical, right? And we know that for radicals, the domain is limited to the inside of the radical. So you can either do x plus 1 is greater than or equal to 0, and you get that x is greater than or equal to negative 1, which is exactly what the range of my function is. So that's my domain, from negative 1 to infinity. Now for the range, yes, it is limited to the domain of my function, but the range of my function is negative infinity to infinity. Now because this is a radical, we know that radicals don't start, are not applicable from negative infinity to infinity. They start at 0 unless there is some kind of vertical transformation. And I do see here that it went down 4, meaning that the range would be from negative 4 to infinity. Let's look at one more question. Here we have a rational function. Okay, for rational functions, the domain and range always just switch places for the the inverse. So I know that for rational functions, we don't know how to find the range of these yet, and that's okay. We don't need to. We just need to find the domain. And we know that for domain, the denominator can never equal to 0. So x plus 6 can never equal to 0. That means that x cannot equal to negative 6. And if I put that on my number line, negative 6 is the only number that is not included. So the domain would be from negative infinity to negative 6, u negative 6 to infinity. So I'm going to keep this in mind because this is going to be the range of my inverse. Let's go ahead now and find the inverse function. So y equals 2x minus 3 over x plus 6. Remember, we switch places, so x is equal to 2y minus 3 over y plus 6. And this is the same type of problem we did earlier. I need to remove this denominator, so I'm going to multiply by y plus 6 to the other side. So now I have this y plus 6, x is equal to 2y minus 3. We distribute this x, so xy plus 6x is equal to 2y minus 3. I only want the terms with the y on the left side, so I'm going to subtract this 2y over, and then I'm going to remove this 6x because I only want the y's on this side. So I'm going to subtract the 6x as well. So now my equation is xy minus 2y is equal to negative 3 minus 6x. On the left side, I see that I have only y values, so I could factor out this y, and I have x minus 2 is equal to negative 3 minus 6x. And then I would divide the x minus 2. Now y is alone, so this is my inverse. So my inverse function is equal to negative 3 minus 6x all over x minus 2. Now to find its domain and range. As I noted here in blue, for rational functions, we're going to find the domain of the function, which is the range of the inverse. I already did that. Then find the inverse and find its domain by setting the denominator not equal to 0. So again, this is another rational function. So to find the domain of my inverse, I take that denominator, x minus 2 cannot equal to 0. So x cannot equal to 2. So that means that the domain of my inverse is from negative infinity to 2, u 2 to infinity. And the range of my inverse is the domain of my function, which is negative infinity to negative 6, u negative 6 to infinity. And that's inverse functions.